Today we have the immense pleasure, and I personally have the immense pleasure of having Professor Sir Kostya Novosolov, who will be dialing in online for a fireside chat on frontier materials, where he sees AI-driven materials discovery. This is also a very personal topic for me as well. So I did my PhD at Manchester in theoretical physics in graphene, and from that time to now, I'm really so stoked that, for example, in the UK, there's an advanced materials strategy. There's more and more interest in this domain, and I'm really excited to see how AI will connect with these topics. So without further ado, if we do a screen change, and Kostya, you'll have to let us know if you can hear us.
Yeah, I can hear you.
Awesome. While the change is happening, my first question is, so it's been 2 decades since the discovery of graphene, and that has, on some level, maybe some will say, has transformed materials science. How do you see the field of frontier materials evolving since that time, and what's most important to you and most interesting to you right now?
Indeed, graphene transformed the field of materials and advanced materials quite dramatically, and actually in many different ways. But I don't want to be seen as an advocate for graphene per se. I've been working with this material, just playing with this material for a number of years. These days it's getting quite actively and rapidly into the applications. But I think the most important, 2 important consequences of graphene appearance, of course, is first of all, is the appearance of the whole family of the 2D materials, which brought us van der Waals heterostructures and the field of the topological materials. So I think this field of topological materials changing the whole perception how we think about materials. So we don't think about materials in terms of the band structure anymore. We really think about topological properties much more, so that those properties become more important, especially in terms of quantum applications. I'm not only talking about quantum computing, but quantum applications in general. So I think
to challenge you on, you're saying that topological materials are really interesting. Would you say this is of scientific interest? How about for those in the audience that maybe you say quantum, but people are thinking, oh, but those applications are so far away. Would you say your interest in topological materials is more on the research side, or you do think there's going to be an impact in industry?
In terms of the research, it definitely changes the whole perception how we do it. But believe me, the applications won't be far away. So we are very serious about replacing silicon with one of the members of the 2D family, with molybdenum sulfide. Many companies work on this, including TSMC. So there are several labs in Singapore which work on various aspects of this technology, including my lab as well. And then of course quantum is another story. So I don't think the quantum story has finished with the cold atoms, with ions and with Josephson. I still think that the quantum story is still has years to go and years to grow, and I don't think we settled on the platform yet.
Thank you, Kostya. In terms of, okay, let's say I give you unlimited resources today. Could you tell us a bit about what you're doing in your lab and what you would do? When I say resources, I don't just mean money. If I gave you all the talent, everything that you need, tell me about what you do in your lab and what you would do with these resources.
I think you're asking the wrong person here. So it's because I'm in Singapore now. I left Manchester same as you some years ago, though my motivation was a little bit different. So I thought that graphene is great and the field of 2D materials, topological materials is fantastic. I just thought that I need to change the direction quite radically. And basically what we're trying to work on is the field of functional and intelligent materials. And we're basically trying to create materials which behave in a similar manner as the biological system. So it means that they can rectify entropy and can create order out of disorder. And so the examples of the materials materials includes those which can do self-healing. Like we have materials where we drill a hole and then this hole completely regrows by itself, gaining energy from the entropy part of the free energy. Smart membranes which can, like ionic transistors, which we can turn into ionic circuits and they behave as artificial heart or artificial nerves, for example. So that's something which interests me personally, which is very academic, I should say, but I still try to keep an eye on what is going on in the area of the applications, especially for the 2D materials.
Thank you, Kostya. Could you touch upon how is robotics or machine learning, AI, how is that influencing your interest and the work that you're doing now?
We are one of the first institutes and groups which started to work on the robotics and the applications of AI for material science. And I should say that over the last 5-6 years, my enthusiasm towards this has been really oscillating quite wildly. So from just complete just ecstasies and just being very optimistic about it to be completely delusional and just thinking about it as a complete disaster. Luckily, you catch me now in quite an optimistic phase. But in reality, what we see that when we start creating those complex materials, say the self-healing materials, we observe this in high entropy alloys. If you try to compute the properties of high entropy alloys, you would fail miserably because those are extremely complex materials without any unit cell at all. The applications of machine learning and dynamic machine learning is something which we develop here in my lab is practically a must. The problem which I see currently that modern materials actually, and not modern, just any materials which we use, is by far more complex than people would put into their databases. If you take steel, it's not iron, right? It's a very complex alloy and the unit cell is huge and we don't have databases for that. So we're trying now alternative methodologies where we use robotic labs, as you mentioned, and we include synthesis as part of the descriptor for our materials. So it's not structure to property relations anymore. It's really starting from the synthesis, which can encompass the morphology of the materials, but also their chemical composition. As I said again, luckily you will catch me at the right moment, so I'm quite optimistic, and we're building quite a number of different robotic labs exactly for this.
Okay, I'd like to open the floor to questions. Hopefully we're asking the right questions here. Does anyone want to ask Kostya a question or have a thought or a comment or even disagree with what Kostya has commented on? Yep, Sadas from SLAC's Third National Laboratory.
So you essentially said that it is going towards lower entropy, like living organisms in biology. So what specifically is driving it? There must be a driving force.
Correct. So basically, first of all, we gain a little bit of the hint from the living systems, and the definition of living systems for a physicist is those which can recuperate entropy and somehow slow down its growth or actually decrease the entropy. In our case, and there are many different types of self-healing materials. So we're trying to work with those which work on as we think, on the most fundamental principles. And so in our case, we prepare those materials in a very strongly disordered state where the entropy part of the free energy is huge. In a sense, their atoms there are strongly intermixed, and those atoms, they don't like to be intermixed. They like to have specific neighbors, and this, which is the enthalpy part of the free functions. And then once we create, but usually those atoms, they cannot swap their positions, because in a crystal it's very difficult to swap the positions of the two atoms. Now when we create a defect like a crack or a hole, now atoms can start to rearrange themselves, and they're moving towards more energetically favorable ordered state. So we basically take the energy from entropy and we turn it into enthalpy part. We understand on the microscopic scale what are the basic principles, what drives this. But if you want to describe it in details on the level of how we understand, say, silicon, you would fail unless you use AI.
Kostya, so Sadas was asking whether it's like amorphous materials becoming crystalline?
No, it's actually both phases are crystalline. It's just one state has much higher entropy and another state got much lower entropy. And this energy from the entropy, it turns it into the enthalpy part. So both are crystallines actually, but the level of entropy is very different.
Thanks, Kostya. We've got a question here from Dr. Fred Roseboom.
I was still wondering, because I also intuitively would say you do still decrease or increase crystallinity or amorphicity, but is there still then at least a relation between short-range ordering and long-range ordering in this sort of material class?
No, so in this case, the crystallinity is exactly the same, the crystal symmetry is exactly the same. But imagine that you grow a high entropy alloy. So in high entropy alloy, you have 10 different elements which are intermixed, but they are in the particular crystalline position. And because you quench them from the high temperature, so they're stuck in this highly disordered, means that many elements are intermixed. They're stuck in this disordered state, but in the crystalline state. Now, in this disordered state, you have copper, iron, cobalt, and they're all next to each other, and they don't like this. They are there only because you quench them and you prepare in this high entropy alloy. They're much better. They much like to split into phases: copper separately, cobalt separately, iron separately. And I'm just simplifying this, but that's the case. But they cannot do this in the crystal state because they cannot swap. Now, if you create a crack, the atoms has freedom to move, and then they start to do phase separation. But during this phase separation, they regrow the defects.
Okay, so I still see some similarity then in between hard magnetic alloys and soft magnetic alloys, where if you quench, you will favor some of these amorphous versus microcrystalline states with grain boundaries formed.
You can think about this in this way, but our experiment are on much smaller spaces. We work within one crystallite, and we show that even within one crystallite, it works exactly the same.
Thanks, Kostya. So to wrap up, you commented earlier that I was asking the wrong question. So to finish off, for everyone in the audience, can you tell us or suggest to us what kind of questions we should be asking, whether we're working in academia or a startup or industry? What is the right questions to ask ourselves?
I think there are two aspects of material science, and one is that we need to develop a good language to describe new materials, and this language needs to be as universal as possible, and that's so I think developing this topological language is actually quite good. But at the same time, when we are talking about, so now we are at a very interesting state of development of the material science and condensed matter physics in general, that when we talk about applications, we don't need to be limited with some existing materials. Now we can actually think about synthetic materials, about composite materials, about heterostructures, and so we can start from the applications and then drive down to what kind of materials do we want to develop for our applications. And that's probably a unique time in history, that we are not limited to silicon or to germanium anymore. So we can produce so many more new materials, again, either composite or heterostructures or alloys or just unique states, that including those for quantum, that I think it will change the way how we're going to do technology.
Thank you, Kostya. Thank you.
Thank you.
Wow.